Hi, everyone. We are Five Star Environmental Solutions. I'm Gabriel,
I'm Jordan.
I'm Elijah.
I'm Olivia.
And I'm Adam.
and this is our project for the water reuse design for the International Wastewater Treatment Plant. In this project, we're going to give you an introduction and a background of the project with design goals and needs and considerations. We're then going to go into the design and we're going to talk about the wastewater treatment portion and specifically nutrient removal. And then we are also going to talk about our design of the advanced water purification, which includes membrane filtration, reverse osmosis, and UV disinfection. And then we're also going to talk about advanced oxidation, which we won't be using in this design, but we will talk about it. And next, we're going to have our key considerations, the irrigation water demands in the local area. We're going to talk about our logistics and sustainability.
The Tijuana River faces major pollution challenges due to a rapidly growing population and aging infrastructure. Currently, the river is contaminated with sewage, sediment, and trash, posing serious health risks to both humans and wildlife. The South Bay International Wastewater Treatment Plant currently has a capacity of about 25 million gallons per day, but during heavy rain events, the incoming flow is often over 25 million gallons per day. So the excess flow is allowed to bypass treatment entirely and is discharged into the Pacific Ocean. This project is a major step towards sustainable water management along the US-Mexico border.
For this design, we have certain goals. This design is made to treat 50 million gallons a day and have a maximum flow rate of 75 million gallons a day, which is much more than what's currently in place. There's going to be 30 million gallons a day of advanced treatment that's going to be outpoured into the Tijuana River. And we're going to have water reuse availability in Tijuana, which they're going to use as irrigation. There's also going to be subsurface storage via groundwater recharge.
Next is our needs and considerations, and we're mainly using the Title 22 requirements. And in the Title 22 California Code of Regulations, it says that for groundwater replenishment reuse projects, no more than a 6 log reduction, and then each process has no less than 1 log reduction for 3 separate process trains. And then additionally, we have other ones like tertiary recycle water removes 99.99% of bacteriophage MS2 poliovirus. And then aside from that, we also had additional considerations like ensuring that we're treating a maximum flow of 75 million gallons per day. It's also highly effective, so we're minimizing lost costs and increasing the performance of our treatment plant. And finally, a political consideration is the 1944 water treatment requirements, and that creates the International Boundary of Water Commission. And that's for kind of like the fact that we're dealing with international borders, international water, and it's going to help guide our treatment.
Now we go into our design. The first step of our design is in the wastewater treatment, and we're going to be dealing with the nutrient removal. This is a two-step process that's going to ensure that the nutrient levels of the effluent are adhering to the regional standards. The first step is nutrient or nitrogen removal, excuse me. That includes nitrification, which is in the aerobic stage, and it converts ammonium to nitrate. And then we have the denitrification, which is in the anoxic stage, and that converts nitrate to nitrogen gas, which is then released into the atmosphere. And for the second step, we have a phosphorus removal, which will occur in the anoxic and aerobic zones. And we chose the Virginia Initiative plant process. We chose that configuration because it was very effective. And in the figure on the right here, you can see all of the nutrient levels as they go through the 3 zones. And then we have our advanced water purification, which consists of 3 steps. And these are all aimed to meet the California Title 22 regulations for landscape irrigation. The first step is membrane filtration, and that aims to remove small particles and microorganisms. Then we have reverse osmosis, which removes all dissolved solids, metals, salts, and pharmaceuticals. Then in the UV disinfection, we aim to remove all microorganisms, including bacteria, viruses, and protozoas. And on the right here, you can see a document or a diagram of the steps that the water will go through. First, the wastewater treatment, then the membrane filtration, then reverse osmosis, UV disinfection, groundwater recharge, and landscape irrigation.
For membrane filtration, we chose the PVDF type. That stands for polyvinyl lighting fluoride, excuse me. This is because PVDF has the best durability and it also has a high free chlorine contact tolerance. And PVDF also has aggressive cleaning and disinfection, so we can make sure that we're keeping up with the maintenance of this treatment plant. We also calculated and found that the online production factor was 0.893, and that's using like time for backwashing and maintenance. The feed flow rate was 93,000 meters cubed per day, and with that, it totaled to an area of 54,506 meters squared, and that's for 1,232 modules, 18 skids, and 77 modules per skid.
Next part of our design is reverse osmosis. Within the reverse osmosis, we're going to have a permeate flow of 20 million gallons per day, and we're going to have a 90% recovery with that. From those values, we're going to get a feed water flow of 22.2 million gallons per day. And this is using the 6-log removal like discussed before. Within this, we have 141,954 square meters of area. And from this system, we're going to have rejected water after it. And so with this rejected water, we're going to need solar evaporation, and we're going to put it back into the ocean as well. That way we have two methods, not just one, to improve that. We have the reverse osmosis arrays right here. This is going to be a 2-to-1 vessel split configuration. As you can see from the figure on the right, we have the first stage there and the second stage. Within the first stage, we're going to have 416 vessels, and the second stage is going to have 208 vessels. This is a total of 624 vessels. And within those, we're going to have 4,368 elements. And each element is going to be around 32.5 square meters, which we designed to be put into 2 skids right there. And those skids are going to have a combined area that takes up 800 square feet.
Next is our UV disinfection, and we found all these values by using the dose response curve for the MS2 virus. By calculating it, we ended up finding that the size of reactor is 101 meters squared, and that's over, you can see that in the plan view right now. We also calculated that the detention time would be 26.3 seconds, and that's for 1,320 lamps. And this is again just to make sure that we're removing the microorganisms, including bacteria, virus, and protozoa, like Gabriel mentioned.
Advanced oxidation processes, or AOPs, go beyond traditional disinfection by combining UV light with strong oxidants like hydrogen peroxide. This powerful combination allows us to achieve a 6-log removal of microorganisms and a 0.5 log removal of contaminants like 1,4-dioxane. What makes AOPs especially important is their ability to fully oxidize synthetic organic compounds, such as pesticides, pharmaceuticals, and industrial chemicals into harmless byproducts like water, carbon dioxide, and mineral acids. Unlike conventional methods like chlorine disinfection or air stripping, which may only transfer pollutants to another phase or leave residuals, AOPs ensure complete destruction at the molecular level. As an example, in the San Diego Pure Water Project, both UV H2O2 and UV HOCl systems were tested. While HOCl worked well at lower doses, UV with hydrogen peroxide proved more effective and stable at larger scales, making it the ideal choice for full-scale water purification. Ultimately, UV AOP with hydrogen peroxide offers a safer, more reliable, and a more sustainable approach to treating complex water contaminants. Next, we're going to go into the key considerations. Let's talk about the logistics of the IWTP upgrade. The total area needed for the advanced purification treatment units, including membrane filtration, UV disinfection, and reverse osmosis, adds up to nearly 280 square meters, as detailed in our appendices. These units will be integrated into the existing layout at the South Bay International Wastewater Treatment Plant, ensuring a compact and efficient site footprint. A proposed layout of these units can be seen on the image on the screen. A key component of the upgrade is groundwater recharge. This will be done using recharge wells, an underground method that directly injects treated water into aquifers. Unlike surface spreading, this subsurface approach allows for more control and requires less land area, while still complying with California Title 22 regulations. To protect public health, monitoring wells will also be installed to track water quality between the recharge and drinking water zones. However, it's important to note that potable reuse, meaning using this water as drinking water, is not yet permitted at IWTP. That's because it doesn't meet California's strict source water control standards, which require extensive upstream monitoring and pollution prevention programs. Until those programs are in place, the water can't be reused for drinking purposes and is limited to landscape irrigation.
With the 20 million gallons per day of water, our calculations show that an area of 6,110 hectares, or roughly 15,000 acres, can be irrigated. And our calculation process began with calculating the landscape coefficient. In doing so, we took into account the water-efficient vegetation, moderate density, and high microclimate factor. With this value, the evapotranspiration for the irrigated area was calculated for each month. Following this, we calculated the monthly water requirement, and we did so by subtracting the evaporation rate by the monthly precipitation rate. And in our table here, the values of 0 mean that the evapotranspiration for the given month was less than the precipitation rate, meaning no extra irrigation was necessary. Following this, we calculated the irrigation rate for each month. We took into account Tijuana's hot and semi-arid climate, the high clay content in the soil, as well as the efficiency of irrigation. From here, we went on to the monthly irrigation requirement, and then we added those values together, giving us the total annual irrigation requirement. And then next, we converted the 20 million gallons per day into meters cubed per year, giving us a total volume, and we divided that by the total irrigation requirement. And this brought us to our value of the 6,110 hectares. Following this, we obtained the total volume of water per month by multiplying the monthly irrigation rate in the area. Sustainability is a crucial part during new development. Sustainability is broken into 3 different pillars: environmental, social, and economic. The environmental aspect was addressed by increasing the volume capacity of the secondary treatment, allowing for lower pollutant levels in nearby water bodies. Additionally, groundwater recharge of the nearby aquifer ensures that no groundwater depletion will occur, maintaining the health of the ecosystem. The economic portion was included in this project by placing a high emphasis on efficient systems that are as cost-effective as possible. High-quality materials were also selected, which saves money in the long run when it comes to maintenance. The social side of sustainability was addressed by sending the water to Tijuana for irrigation. Currently, Tijuana is facing water scarcity issues, and this will enhance water security for the people. This will also directly benefit the residents by lessening water supply interruptions and helping the city meet the ever-growing demand for water. The irrigation will also be used for urban greening, contributing to the well-being of people. Our project also addresses United Nations Sustainable Development Goals, or SDGs, specifically Goals 6 and 14, clean water and sanitation, and life below water. Our project addresses the sub-goals 6.3 through 6.5, which include reducing pollution in untreated water, increasing water reuse, ensuring sustainable water withdrawals, shrinking water security, and enhancing transboundary cooperation between the United States and Mexico, as seen through the IBWC.
And here are the references that we use for our project and our report. And if you want to look at the report, it gives you more detailed calculations and it goes into depth about all the things that we talked about today. Thank you for watching our video, and we look forward to hearing from you if you have any questions. Thank you.